So when we're looking at our enolates, okay, with our enolates, what we need to be addressing is how these things happen and deciding between kinetic and thermodynamic. So first and foremost, all we're doing is removing a single hydrogen from our starting ketone, and it has to be an asymmetric ketone. There are two potential hydrogens we could remove. Okay? We can call it our top hydrogen or blue hydrogen, or our red hydrogen or our bottom hydrogen. Okay? Those result in two different enolates. Okay? Those enolates then have reactivity that can potentially continue on. So what we're looking at here is starting with the same reactant and then going through to form our product. Okay? That product is now just our active enolate. Okay? So we can call this our red intermediate versus our blue. Okay. What would we expect? Okay. Higher or lower energy? So let's pick one. Red or blue? Red. Okay. Would I expect that to be lower in energy or higher in energy than our reactants? Higher. Why would that go higher? It has charge. Okay, so we can put it up. Where's the blue one? Okay, it should be higher in energy than the reactant. Should it be higher than our red one or lower than our red one? Why should it be higher? What we're referencing is the substitution of our alkene. Why do we need to look at the resonance contributor? Because that's the better resonance contributor. So that then means our blue product is a little bit higher in energy. If we were to connect these now, we might expect something along these lines. Okay? Where the red one has a lower transition state. Okay? That would be our initial expectation. And yet we don't find that to be true. What we actually find to be true is that the red one has a higher transition state than the blue one. Why is that the case? Okay. What we're talking about is the transition state. The transition state is the base coming in to react with those hydrogens. To react with the red hydrogen, what does our base need to get near? What's next to that red hydrogen? A methyl group. Okay. That methyl group ultimately has what? A lot of electrons. So as the base gets in close to that hydrogen, it encounters a bunch of electrons, which then means what happens to the energy of that transition? It goes higher in energy. So our transition state becomes higher because of a steric repulsion. Okay, sterics with our base. What happens in the case of the kinetic one, the blue one? Well, now there's less stuff around it. Okay, we could say that this has less steric hindrance, and because of that, that transition state drops in energy, and we see this shift, and we see two potential products come out of this, one being kinetic and one being thermodynamic. Which product are we going to get first? We'll always get the kinetic product first. Okay, so if we're looking at this, okay, and I will make this more complicated in just a second, so you better ask questions. Okay. When we run our reaction, okay, we will form the kinetic product first. Okay. If we are at low temperatures, what happens at low temperatures? We can only form the kinetic. Why can we only form the kinetic? At low temperatures, there's not enough energy to reverse this reaction becomes irreversible. Okay, so at low temps, low T, we get reactant going to K. What happens if we increase the temperature? Okay, and this is where it's going to get really complicated here. Okay, but we're going to try and show this fully out. What happens at high temperatures? There's the reversibility of K. So the first thing that happens at high temperatures is what? I form the kinetic product. But because I'm at high temperatures, what can happen? I can reverse back to the reactant. Because I'm at high temperatures, does it all go to K. No, some of it could go immediately to form the thermodynamic. Okay? And that is technically happening with the top one too. But if we were going to use arrows to represent this, that's what's happening in the top case. A very, very tiny amount goes to make the thermodynamic. Okay? Such a small amount that it becomes irrelevant. When we move to higher temperatures, we get a significantly larger amount going to form thermodynamic. I'm still forming kinetic. Okay? Because the thermodynamic is irreversible at high temperatures, what ultimately happens in our reaction? If we give our reaction enough time and heat, everything becomes the thermodynamic. Because if we're looking at a balance, the reactant goes out to make kinetic and thermodynamic. Thermodynamic is done, it's now pulled out of the system. We've now formed some kinetic product, but what can the kinetic do? It could reverse to form reactant, but then the reactant becomes thermodynamic and it can't reverse anymore. So what we end up seeing is a slow siphoning of the reactant concentration out towards the thermodynamic product that is now irreversible. As the reactant concentration goes down, what happens to the equilibrium between our reactant and our kinetic product? As I drop the concentration of reactant, what happens to that equilibrium? It shifts to make more reactant. As more reactant's formed, some of it still siphons out to form permanently the thermodynamic. Kind of makes sense? Okay, so when we're looking at temperatures, this is what's happening. It's a balance between these two effectively competing reactions. At low temperatures, the amount of thermodynamic product is so small that it doesn't affect the overall reaction. At high enough temperatures, it now makes a significant impact, both in the formation of the thermodynamic and, more importantly, the reversibility of the formation of the kinetic product. Kind of make sense? Okay, so first your question, and then I'm going to ask a confusing one.
So I think we talked about this a little bit last time, but to clarify again, so when you get to the intermediate there, why is the blue the higher energy? Because there's a negative on a secondary, which is going to be more stable than...
Between the two resonance structures, so let's pick, let's go all the way up to the top. So I'll have to box them in.
Because I thought we evaluated charge before resonance.
So when we go through and evaluate those two structures, what we're trying to decide is between those two, which one is more important, which is the best structure to be looking at. Okay? Said another way, should I be using this structure to explain the reactivity of this molecule? Anybody know what that molecule is? CO2, also known as carbon dioxide. Should I be using that structure to explain the reactivity of carbon dioxide? Why not? What's the better one look like? Double bonds both directions. In this case, the difference there is obvious, quote unquote. One is neutral, one is charged. Okay, so if I'm going to look at the reactivity for this molecule, I'm going to focus solely on the blue one here, not color-coded, okay, because it's neutral and this one's charged. Okay? Are those resonance contributors of each other? Yes. Can I use the red one to help me predict something about the reactivity of CO2? Yes. Okay? So when we go back up to our blue box, we're looking at those two resonance contributors. We're trying to decide which one should I be using to evaluate stability.
Okay.
Okay?
Those are both technically intermediates, right?
They're both the same structure.
They're both the same.
Just like down here, they're the same structure as CO2. Okay, so now the question is, which one should we be looking at? Okay, and if I just drew out the red one and asked you to predict something about reactivity, you could probably do it from the red one. But if we drew the blue one, or for that matter, how many of you would even draw the red one as a valid resonance structure? Most people don't see it, and that's ultimately because of how you were taught resonance. When we're looking at resonance, we have to evaluate both and decide, is there a difference? Yes, that difference puts the negative charge on the oxygen. That's the most stable one. That's where I need to look and do the comparison there. Okay? After that is then what's the most reactive thing? The pi bond. The red one is a more substituted pi bond. The more substituted pi bond, the more stable. Yes?
So is kinetic stable with thermodynamic?
So, and this is going to get, what are you referencing? Okay. Is the kinetic product the likely one to form?
Yes, because of
Okay.
temperature.
Well, at low temperatures, kinetic is absolutely going to form. What happens at high temperatures?
The
Thermodynamic. So we can't just say, oh, well, it's kinetic. Maybe. What are your conditions under which that thing happens?
So under low temperature conditions, kinetic would be.
At low temperature, we expect the kinetic. At high temperature, we expect the thermodynamic.
But does stability have anything to do with that?
Stability is what's allowing us to decide which one's thermodynamic and which one's kinetic.
So
Okay.
you wrote something.
And when we go through and look at it, the blue one is higher in energy than the red one, which would mean which one's more stable?
The lower energy.
The lower energy. The red one, the thermodynamic product or the thermodynamic enolate, is always the most stable. That doesn't mean it's the one that's formed. Okay, those are two separate conversations. Kind of make sense?
Yeah.
Okay. Is the kinetic product irreversible? What do you mean you get it?
It's depending on the condition, it's reversible.
I can't make the statement that the kinetic product is irreversible. Okay? Because depending on the circumstance, so I was waiting for someone to just commit and say yes or no, I would have said the other answer. Okay? The kinetic product is the product at low temperatures. Okay? At high temperatures, it's not. It's now the thermodynamic. So when we're referencing which one we get, we have to be very careful to reference the conditions under which our enolate is forming. Make sense? Okay. So I'm going to clear virtually everything and painfully slowly. No, I'm not. I'm going to clear everything. No, I'm going to do it slowly. So let's just pause. Was it only a minute ago?
No, never knows.
What?
Now you're erasing the whole slide.
Yeah. Where we went up and drew the. Thanks, Mo. What's the fourth base? We have oxygen, we have hydride, we have nitrogen. Ethane oxide is still oxide as the base. What is a characteristic of a base?
Charge.
What charge?
Negative.
What do you see right there? You have a carbon that's negative. Depending on how negative the carbon is, it becomes stupidly strong. Okay? As a carbanion. Believe it or not, our enolate is not stupidly strong. It's just strong. Okay? But depending on the negative carbon that we produce, we can get a stupidly strong or we can just get a strong. Okay? That's where I would argue you need to come in with the memorization and say, here's the line, because it is an arbitrary line. Okay? As far as we're concerned, because we don't want to evaluate the quantum mechanics of it. Okay? And not every carbanion is strong or stupidly strong. Yep. We'll see that line when we encounter it, believe it or not. Okay, which isn't quite yet, so we don't need to panic quite perfectly. Okay, just because I think I saw some people referencing it. That picture. Did anybody actually recognize that picture? Yeah, it's Dr. Strangelove. Okay, which I usually tie in with anything that's just weird and crazy. If you watch the movie, it's weird and crazy. You'll understand. Dr. Strangelove. Yeah. So, ta-da! This is mostly the rest of the next 2 units. Okay, this covers all the big ones. And if we go through and look at these, what ends up being our nucleophile in a lot of these? Carbon. Okay, so it's a question of how strong is our negative carbon and how does it evaluate each of those reactions. Okay, so we will see all of these by the end of the semester. You might start working on it.
What chapter is this?
We're looking at 17, 18, 19 is our next big unit. Okay, Because, unfortunately, we burned too much time with me screwing up, I'm not going to go over these practice ones. I would recommend you go through and take a look at them, okay? Because they could easily show up as test questions. So if you've got questions about them, you can ask me in office hours. Okay. The synthesis activity, I have not had time to make a better copy for all of those. Okay. As soon as I get that, we'll go back to it. But I want to kind of walk through some of the basics behind it. Okay. The biggest things to evaluate, and I'm not even sure, I don't think I've even posted it to Canvas, but it should show up on Canvas under Files. Okay. It is highly encouraged that you go through and look at those syntheses. Okay. Those syntheses will show up on the next exam. This is officially Chapter 13. There's virtually no content in Chapter 13. Okay. What it is what I've got put up in the synthesis activity. They're guidelines and steps on what you should think about when you go through and complete a synthesis. Okay. So, where's the chemistry? Look at your starting structure and try and predict where's the most likely bond to make. Because if that's the most likely bond to make, it is probably also the most likely bond to break. Right? So we could think about the chemistry by identifying that position. Okay? We do it in both the starting structure and the final structure. The next part is look at those two things, those differences, and say, can I do that in a single reaction? Okay? If you can, and it's a synthesis question, you're probably doing it wrong. Okay? Because synthesis questions usually take at least 2 steps, if not 3 or 4. Okay? What do I mean by the types of reactions? Is it an acid-base? Is it a substitution, elimination, addition, radicals? Okay? So we had that summary slide at the very beginning of the semester on what each of those things are. That should be committed to memory because you can use that to help categorize reagents. Okay? What atoms or elements are missing? Okay? So if you look at a step and say, I need to do an elimination. Well, an elimination requires a leaving group. I don't have a leaving group. Put a leaving group on the structure. How did you get that leaving group onto the structure? So it's thinking about those missing pieces and just putting them in at first. Once you've put them in, you now have to test yourself. Okay? Reverse the reaction and say, hey, would that actually do what I want it to do? Or is it going to do something else? Okay? The last thing, which is typically what everybody tries to jump to and which is why you ultimately all fail at it, and by you, I mean me as well, okay? Consider the actual reagents. Okay? You may look at it and be like, I need to add H and Br, but it's adding in a way I don't know how to add. Okay? In a show your work, what should you do? Add HBr, but don't do it in a normal way. You've proven you understand what needs to happen, you just don't have the reagent knowledge yet. Do you need the reagent knowledge to complete a synthesis question? Yes, absolutely. This is one of the reasons why memorization becomes important. Some reagents you need to know, and it's typically the ones that don't do standard chemistry, because the standard chemistry becomes obvious if you follow the patterns. Does that make sense?
What reagents do we need to know?
Every single one we've talked about over the last 4 months. 4 months? We've only been here for a month. First semester. Every single reagent.
With the list for it together.
It's called the end of each chapter in your textbook. Yeah. And if you're using the Cardy textbook, if you flip all the way to the very end, one of the appendices, they list all of the reactions. Okay? Synthesis takes practice. Okay? And it will help you memorize your reagents. Okay? So, we want to complete this reaction. Okay? One of the things that we need to watch out for, okay, which I didn't mention yet, is we have to watch out for constraints. Okay, where is it? Right here. Constraints. So in the way this question is phrased, well, there's not really saying there's any constraints. Okay, so I'm going to make it more difficult. I'm going to say the only source of carbon, the only place you can bring in carbons is this guy. Huh? So when you try and go from the bromide to the ether, you'll notice that we have differing carbons, right? The only place you can get carbon is from the bromide. For all of this synthesis. So every synthesis has its own limitations. All right, so what do you notice? Okay, so we got 6 carbons here and 3 carbons over here, which means
Probably some sort of coordination.
I'm going to have to be splitting this up. I'm going to be looking at one piece with 3 carbons, and I'll be looking at another piece with 3 carbons. Right? And then somehow or another, those two need to come together to make our final product. Yeah? Kind of, sort of? Okay. Where's the chemistry in my starting structure? Pause. Never mind. Lie. Well, not never mind. Double back. Starting structure had how many carbons? There's 3. Where are those 3 carbons in our product? 3 on the left, 3 on the right. Okay? Because we've got the ability to color code, we'll call them the purple 3 and we'll call them the blue 3. Which one do you want to look at first? Blue 3. Okay? What's the difference between the blue 3 on the left and the blue 3 on the right? Where's the chemistry in our reactant? Where is it? In our reactant, it's at position 2, right? Right there. Where is it in our product? Right. Interestingly enough, it's at position 1, position 2, and position 3. Why'd you say 3?
Because it's getting attached to the ester oxygen.
Right idea, ether, oxygen.
Ether.
Right, so all 3 positions need to be reactive. Okay? Can I take my starting structure and make all 3 positions reactive in a single step? No. Okay? So what do you want to try? What would substitution do? Does that change the reactivity at the different carbons? I could put something on there that withdraws electrons. What is the bromine doing? Withdrawing electrons. So if I did a substitution, does that change the location of the chemistry? No, it keeps it identical. Which means substitution's a crap reaction to run. Don't do it. Okay. What about acid-base? Do I have any acidic hydrogens? And if so, where would those acidic hydrogens be? What's that?
What about the second carbon? Is that H slightly acidic?
Like off that end? Why would that H be acidic?
Induction.
Okay, an inductive effect. Right? That could explain the acidity. That gets us a negative carbon. Is a negative carbon something that is stable? No. Is induction going to help that? No. So as a strict acid-base reaction, and yes, I'm emphasizing the strict, no good. So acid-base is out. How about an addition reaction? Let's add something to this. What do you need to do an addition reaction? No, you do not need a leaving group for an addition reaction. You need a what? Alkene's a good first step. I would say that's too narrow. What are you actually referencing? A pi bond. Do we have a pi bond? No, so we can't do substitution, can't do acid-base, can't do addition. Acid-base on its own formed an unstable negative carbon. Okay. Radicals. Does anybody want to do radicals? No? Okay, cool. So not radicals. That means we only have one reaction left, which would be, Mo? Elimination. If we did an elimination, what happens? What are we eliminating? What would be the product in an elimination reaction? A pi bond. What am I trying to make in this first piece? What do I need? A pi bond. Maybe a pi bond would be a good thing to put on the structure. How would I go through and get that pi bond to form? What has to happen? What was eliminated from this molecule? The hydrogen and bromine. We just addressed the hydrogen isn't easy to pull off on its own. So what could we add to help get that hydrogen to be removed? We could add a strong base. Okay, whoops, base. We could add heat. What if I picked hydroxide as my strong base? Describe hydroxide to me. Keep using words. Strong base was a good place to start. Keep going. It has a charge. Keep going.
When it grabs that hydrogen, it becomes phosphor, and phosphor is a good leaving group.
Hydroxide is probably one of our smaller bases. What becomes an issue if we have a small base?
Is it everything?
It becomes a nucleophile. Do I have a secondary substrate that's available for nucleophilic attack? Yes. Do I want to use hydroxide? No, because that'll bring in substitution as an issue. I don't want substitution, I want elimination. So what base can I add to limit that nucleophilic attack? I could use T-butoxide. I could use sodium hydride. I could use LDA. All of those are valid bases that would help remove that hydrogen to help get us the elimination product. Cool. This now gets chemistry at 2 positions. I need chemistry at that 3rd. How can I get chemistry at that 3rd position? Okay. We could try LDA because you're trying to do what? Remove a hydrogen. Okay. Problem with that? No, that's not even necessarily the issue. We're trying to remove that hydrogen to make it negative, right? So then our negative carbon would attack a negative oxygen, and that's kind of questionable. What charge likely do I want on that carbon? A positive charge, so an oxygen could come in and attack. Okay? So a strong base like LDA might deprotonate it. The balance there isn't all that good. It's still probably not going to deprotonate it anyway to get you the negative, but it's a good place to start. So base didn't work. I need that to be positive, which means what has to happen? I have to lose H minus. Okay? Because that carbon needs to become positive. Okay? I'm looking at ultimately the reactivity of what functional group? An alkane. And how do I get alkanes to react? Yes, alkanes do react. They're very difficult to get them to react, so I need to do something radical. In that radical process, I'm going to do bromine, okay, in the presence of ROR, okay, or light. Okay, what happens? I get the radical substitution at the allylic position. I wouldn't be able to put the bromine on in the initial structure because those hydrogens aren't as active. At best, if I tried to do the radical reaction at the very beginning, I would have put 2 bromine, or I put another bromine at the most substituted position. Okay. By getting the pi bond first, I can now put that chemistry together. This gets me my positive carbon, which could potentially react with an oxygen off of my second piece. Does my second piece have an oxygen on it? No. Where's the oxygen connected in my second piece? 3rd carbon or 1st carbon, doesn't really matter which one we label. Where's the chemistry in my starting structure? At the 2nd carbon. Does my chemistry have to move places? Yes. Does substitution allow chemistry to move? No. Does addition? No. Acid base? No. First, you'd have to initiate it to get the rearrangement. So one of the reasons why I'm just saying no is because what do I expect you to already have done?
Gone through and tried it.
Looked at those 5 steps of reactions, and I expect you to know those inside and out, which is what I said at least twice at the beginning of the semester. You have to know those 5 bulk reactions. Otherwise, you have to know the reagents that make these jumps. There's only 2 routes. Okay? Why does substitution not work? Because we got a request. Where does substitution do chemistry? Where the chemistry is already located. Do I want it there? No. We even had a suggestion of a rearrangement. So hell with it. Let's just say it rearranges. Bromine leaves. I have a carbocation. Let's rearrange.
I'm not saying right now rearrange.
That's fine. What would happen? We'd form a primary carbocation. So we can't get a rearrangement out of the gate. And even then, a rearrangement is a specific intermediate in one of the reaction types. Okay? So substitution doesn't work. Can addition? Why not?
Because you're removing a pi bond and you need to put
Do we have a pi bond? No. That's why addition doesn't work. Okay, acid-base. The acid-base, again, doesn't work on its own because we'd form an unstable carbanion. Okay? Radicals. At best, if we did a radical reaction, it's going to place our bromine at the most substituted position, which is putting it, again, at the 2 position. I don't want it there. So how can I get chemistry to move? Elimination. Which of my 5 reactions allows chemistry to move from one position to another? Elimination. It's the only one. Okay? You form a pi bond, which is why you get chemistry to move. You now get positions where both of those are reactive. And we would end up with this structure. Cool, we now have chemistry at our 1 position. What reagent are we going to use, by the way, to do that? Same thing as before, a strong base. Ideally, we get specific with our base. T-butoxide works. Okay? Now what do I want to happen? What do I want to add? Okay, I want an OH. Where do I want that OH to be? I want it to be at the primary position. Is that, why do I know I need an oxygen? Okay? So this is a lot of looking back and forth. And I'm fully aware this is a lot. This is what you have to work through. Okay? You have to be thinking about looking back and forth. Okay? And it's constantly thinking back to those 5 reaction types and saying, what allows me to move forward? Okay? It takes time and practice. Okay? I need that position to have an oxygen on it so that that oxygen could become what charge? Negative, so that it could attack that position to kick out the bromine to give me the final ether. Okay? In what type of synthesis? I know that was a mean question because I never test you on names. It's a Williamson ether synthesis. Okay? So I want an OH at the 1 position. Okay? So if I add an OH, where would I expect that OH to go? What charge would that OH likely be? Negative. Where would the negative most likely go? Position 1 or position 2? Why position 2? Position 2 has the more positive carbon. Okay? Because if I draw out resonance, I build the negative charge at position 1, which means if I add the oxygen, it puts the oxygen in the wrong place. Conveniently, I memorized, because Mike said the ones that are exceptions to our standard pattern, we should memorize. And in that, what did I say? It's quite all right. I didn't expect anybody to listen to me. I'm used to it by now. To everything I say, not just, I know you hear some of it, just not everything. BH3, THF, followed by H2O2 and hydroxide. What happens? Okay. I get the opposite addition of the H and the OH. Technically, what reaction did I just run? An addition reaction. So again, finding the patterns can help you go through and classify those reagents. That oxygen needs to attack that carbon. Can that oxygen attack it yet? Rhymes with snow. No, why not? Should I start saying rhymes with cocaine? Would that be bad? No. Sorry, it's been a long day. How do we remove that hydrogen to make that oxygen a better nucleophile? I should add a base. When I add a base, what happens? I now have a strong nucleophile. That strong nucleophile can now attack, kick out my bromine leaving group. Ta-da! And that was only 1, 2, 3, 4, maybe 5 if you want to count that, 6, 7 steps. Okay. This is a more advanced one because I want you to see the pieces and start to recognize how to put things together. Okay. If you want practice, that synthesis activity, the step 1 or the page 1, whatever they're called, okay, those tend to happen in 2 steps. Page 2 and page 3 start to become more and more complicated. For those of you wondering what questions I might put on a test for synthesis, they're probably questions that I know everybody has access to, like from the synthesis activity. Okay? So it would be a good idea to practice those on your free time as well as in class, but we're not doing that today. Okay? Breathe deep. It's not bad or that bad. We could go through and do one like this. Okay. Immediately, you should be saying, what's your step 1 going to be? Say it again. Good. Identifying the type of reaction. Okay. I would argue it's even easier than that. Where's the chemistry in your starting structure? What functional group is in your starting structure? Rhymes with pain. An alkane. Are alkanes reactive? Come on, that was right. Are alkanes reactive? No, what do you have to do? Make it reactive by doing what? You have to do something radical. Yep, the only way alkanes can react is through radicals. Okay. We don't have to use NBS, and officially we should throw light down there too. Could have just used BR2 and more. Okay. Now we could make the argument, okay, now I have reactivity, now I can start to consider. What's the difference between my starting structure and the product? Where's the chemistry? What's that? Which one? Product or reactant? Okay. You're saying there's chemistry right there?
Oh, I was talking about the top one.
Okay, well, so, and we can do that too. You're saying there's chemistry right there?
That's where you want it.
Ah, so what you're referencing is not where chemistry is, you're referencing where chemistry wants to be. You're saying we want chemistry there. That's where I want chemistry. Is the chemistry there right now? No. Where is the chemistry right now? The carbon next to it. You mean the chemistry needs to shift locations?
Sounds like elimination.
That sounds like an elimination reaction. Right? I don't even have to know what the reaction is. I can just say elimination. Okay? Where do I want it to eliminate? I don't even need that detail. Where do I want my pi bond to form? I want it to form out to the methyl. Now what happens? Okay. Ideally, I'd want to do an addition. Do I have the ability to do that addition? You actually don't have the ability to do this reaction, believe it or not. Okay. Can we just straight up add a carbonyl to that position? No. Okay? We could get part way. Okay? We could add, let's simplify this to chemistry you do know. Instead of making it a carbonyl, let's make it an OH. Can I do that reaction now?
You could convert that to a carbonyl.
We can convert that to a carbonyl, you just don't know that chemistry yet. Okay? And as we move through the semester, when we learn new reactions, what do you have to do? Store it so you can do synthesis with it. Okay? Can we do an addition to go from here to here? Is that a single step? Yep. What have I added? Why BH3 and THF? I'm noticing a pattern. It's going to the least substituted. Okay. How do I do the elimination? Strong base. Hydroxide. Hydroxide will actually do an elimination. It won't do a substitution. Why won't it do a substitution? This is a strong base or nucleophile attacking a tertiary substrate. The tertiary substrate doesn't run under SN2 conditions. So I actually won't get substitution. I will get the elimination. Where will the elimination happen? It'll happen internally. Where do I want the elimination to happen? Externally. So I can't use hydroxide. What do I need? I need the sterically hindered T-butoxide.
Wait, hold on. So you said tertiary does not work under SN2.
If we add hydroxide, the result we get is an elimination. It's the internal pi bond. We won't get substitution. We will get an elimination, but it's going to form the more substituted pi bond. We need the less substituted pi bond to form. Only butoxide will work. Is there another way you could complete that one? Chapter 10. Is there another way we could complete that elimination to get the more or the less substituted pi bond? We could theoretically actually get a carbonyl out there now. Because, yeah, we could do something with oxidative cleavage. But that's a lot more difficult, so I don't want to do that. Just the elimination here. This is the least stable pi bond, right? Also known as which type of elimination? Hoffman elimination. Hoffman elimination works really well when our leaving group is nope, it has to be big. The nitrogen, remember our nitrogen elimination? Yeah, that nitrogen with the 3 methyl groups around it. So we could convert this through a Hoffman elimination with an amine. Arguably this is better because it's faster and shorter steps. Okay? Kind of, sort of?
Why don't you call it to the instead?
Because it's not easy for you guys to do the carbonyl. Yeah. That reaction you don't know yet. To get that aldehyde, you can use PCC. NaH for this step? Yeah, that would be acceptable. Why? NaH is not just a strong base. I don't want just a strong base. What do I want? I don't even want stupidly strong. That's not relevant. I want big. Sodium hydride is a big base. That's why it works. Huh? What are you trying to remove? And? And that hydrogen, is that hydrogen acidic? No. So we need a strong base to remove that hydrogen. When that hydrogen gets removed, that's what kicks out our leaving group. Can you stabilize a negative carbon? No. That's why it's not acidic. Okay, and with that, chapter 17. And in fact, the end of chapter 17, I think, is when we see that oxidizing agent. So this is the rough section development for each of these ideas. Okay, we'll look at the general idea behind carbonyls, okay, and address why they're different than our alkenes. Okay, then we're going to have hydride attack. Why would hydride attack a carbonyl? Hydrides are negatively charged. They're strong bases and potentially nucleophiles if you substitute them right. Okay, then we'll have carbon nucleophiles. This is where we encounter that carbon being stupidly strong versus just strong. And then in chapter 18, we see the just strong nucleophiles, our oxygen and our nitrogen attempts at attacking. So chapter 17 is pretty much just throw really, really stupidly strong stuff at it and see what happens. And then chapter 18 says what happens if we weaken the strength of those nucleophiles a little bit. How does that change our perspective on it? Okay, so I always forget about this stuff because everybody likes to know relevance. Okay, why do we like this? I know, right? It's silly. Why would anybody care? Carbonyls, aldehydes, ketones, very common in biological systems. Okay, they derive a lot of the scents, smells, flavors, all that kind of fun stuff that we're used to. We also see them show up in our hormones as well. Okay, anybody know why or how the name? This is named carbone. You break that name down for me?
O for ketone.
Yeah, that's about the extent of it. Okay, yeah. You will see a lot of common names float in with these. Why common names? Those common names become more popular with older chemistry. Okay, older chemistry, these are scents, things that we could smell. So these things were isolated long time ago and then marketed for those scents. Okay, before we had an IUPAC system to go through and name things. So you might see reference to some kind of other kind of names. That's ultimately what's happening. It's a historical feature. Okay, feature. When we look at actual nomenclature, you guys want to take a swing at any one of those? No, I like that. Okay, those are structures that you should be able to name. The big ones that you're dealing with, aldehydes are highest priority right now, as far as you guys are concerned for this chapter. That ends the name in AL or AL. If it's a ketone, we end in ONE. If there's something higher in priority, regardless of aldehyde or ketone, it gets called the oxo. Okay? So, where's the chemistry? Okay, why is the carbon reactive? Why is the carbon partially positive? Because if we look at a resonance structure, we can see that the electrons should shuttle to the oxygen first and foremost, which means we get a very large formal positive charge appearing on the carbon and a large negative charge appearing on the oxygen. So we get a partial negative oxygen and a partial positive carbon. Okay? This is a pi bond. So we might predict the pi bond to act similarly to our other pi bonds, like the nonpolar pi bonds. And in those cases, they acted as nucleophiles. Okay? For that to happen, our oxygen must be willing to share electrons. Turns out it can't happen. Okay? Our oxygen is not nucleophilic. It is mildly basic, but that is the extent of its chemistry. Okay? What happens to the carbon? If the oxygen is our electron source and is basic, our carbon would then become?
Neutral.
Sorry?
Neutral.
No, it's partially positive. It would be an electrophile.
Wait, you just said that the oxygen is not nucleophilic, but the carbon is electrophilic?
Yep. Why is the carbon electrophilic?
Because it has the big portion charge.
Yes.
But the
And the
oxygen's not nucleophilic.
Oxygen is not nucleophilic because those electrons are already being occupied by the carbon. Okay, so those electrons don't have the freedom that the carbon would have to be attacked.
How can the carbon be electrophilic if the oxygen?
We're not talking about relative strength of each of those, so don't weigh that into this. Okay? The oxygen's not nucleophilic because its electrons are already being occupied by the carbon. The carbon can become electrophilic because what does it have?
Then the oxygen can.
It has a weak pi bond that can very quickly break, okay, and go on to the oxygen. Okay, but that weak pi bond is still present and can't break on its own. Something must force it to break. That's why we have the electrophilic carbon. What else is chemistry with this? We do actually have acidic hydrogens. Okay, at this stage, we don't need to stress about those, at least right away. Our primary focus within this unit is going to be that electrophilic carbon. What is that electrophilic carbon going to react with? It's going to react with something negative. Okay, could that something negative be a base? That was gross. Sorry. It's negatively charged. Could it act as a base by reacting with that carbon? No. Why can it not act as a base when it reacts with the carbon?
Because OH is too small.
What is the definition of a base? Reacts with hydrogen. It's not reacting with hydrogen. It's reacting with the carbon. By definition, this is a nucleophile. Okay? When we run that reaction, what would we expect to see as a product? All at once, I like it when you all shout out answers. It makes me feel good inside. That wasn't that difficult to explain. That was a pretty solid explanation. I liked that. Okay, so we could put the OH down there. I switched it up to make it the nucleophile because our OH is officially in the next chapter. And we've now done our reaction. We could go through and protonate at a second stage here. Okay, by adding H+. Now I want you to describe the reaction to me. Beginning to end, what kind of reaction did I do? I did an addition reaction. Is this the same as our standard additions that we've seen?
No.
Why not? We did it with a polar pi bond. How did that change our chemistry? When we had a non-polar pi bond, what happened? Yep, which will still be a problem. A non-polar pi bond, what did it react with? Give me an addition reaction with an alkene. Any reagent. Trying to be fair and share. One person said HCl, one said HBr. All right, we did an addition. What was the first step of that addition? The pi bond attacks the hydrogen. What was the first step with our carbonyl reaction? The nucleophile attacks. What's our difference? This was a nucleophile attacking our pi bond versus the pi bond attacking an, I'll accept two answers, an electrophile. What we're talking about now is a nucleophilic addition. Nucleophiles attacking our pi bonds. The only reason they would attack the pi bond is because that pi bond is polarized. We don't see nucleophile additions with alkenes because they aren't polarized. Okay, which means that would be a nucleophile attacking electrons. That doesn't happen. Carbonyls are great because they're polarized already because of that oxygen. Nucleophiles can come in and attack. So everything we're looking at in this section is nucleophiles adding to a nonpolar pi bond. Does it have to be oxygen? We're going to clear everything. Okay. What else would cause that bond to be polar? Could it be a hydrogen? No, why not? Breaks the octet. Okay, fine. Could it be carbon? No, why not? It's nonpolar. We already talked about oxygen. We could do sulfur. Let's not do that one, though. Nitrogen. Is nitrogen more electronegative than carbon? Yes. So guess what? When we talk about carbonyl chemistry, we're also talking about imine chemistry. Imines are the reference of the nitrogen with the carbon. Right? Why does the nitrogen chemistry get a little bit more different? How many bonds does nitrogen need to be happy? 3. So we're typically looking at another R group coming off of it with only one lone pair. Okay? But all the reactions we're talking about will apply to both imines and carbonyls. Okay? So 17 strong nucleophiles. Hydride, carbon as a Grignard, carbon as a acetylide, carbon as a Wittig, carbon as Gilman. Anybody knows anything interesting about those carbon nucleophiles? They have stupid names. Why do they have stupid names? It's really hard to make a nucleophilic carbon. Okay? Nearly all of them are named. The acetylide one isn't. But nearly all the other ones are named because we have a nucleophilic carbon. That's hard to do. Okay, so they almost always get a special name associated with them. We then move to chapter 18, which is our weak nucleophiles. Oxygen, nitrogen, we throw in cyanide just to be fun. Which atom is the nucleophile, carbon or nitrogen? Why is carbon the nucleophile? If we go through and look at the Lewis structure, there's a triple bond in there. Both of them have lone pairs, but the carbon is negatively charged. Our nucleophile is the carbon. Okay? Why would that be a weaker nucleophile than most carbons? If it can't stabilize the charge, does that make it weaker or stronger? If it cannot stabilize the charge, is it a weak or a strong? It's strong. If it can't stabilize it, what does it need to do? Go to something to make it stable. So if it's not stable, it's more active. Okay? Why is the negative carbon in cyanide more stable than a negative carbon, say, on a methyl? There's no resonance. It's not charge. Is it size? Carbon versus carbon. We can make an inductive argument, and we can make a hybridization argument. It's sp versus sp3. We'll also see carbons coming from our enolates acting as nucleophiles. Those are where it gets really exciting because you get both the kinetic and thermodynamic enolates attacking now effectively themselves. So extra fun. Unfortunately, we got to stop because I didn't bring in the super glue today.